Please welcome the Chief Executive Officer at Synchron Incorporated, Tom Oxley.
Good morning. A little bit of a change of pace from space to brains, although I don't see a B in the Mars acronym, but maybe that'll change soon. I'm Tom Oxley, I'm the CEO of Synchron, and we have built a brain-computer interface. So a few months ago, I surrendered the password to my Twitter account, and I let a person with paralysis tweet out their thoughts. But I mean that literally. You see, Philip O'Keefe can't use his fingers to type like you or I, but thanks to a tiny brain implant, he was able to send the following tweets. Hello world, short tweet, monumental progress. No need for keystrokes or voices. I created this tweet just by thinking it. And then finally, my hope is that I'm paving the way for people to tweet through thoughts, Phil. Now I know what you're thinking. There are people out there who should not be allowed to tweet directly from their brain. I agree. But for people with paralysis and disability, well, this technology can be completely life-changing. I'm a neurologist and neuroscientist. I've been passionate about the brain since the age of 13, predominantly with what I think personally is the most profound question facing humanity: how does the brain manifest consciousness? But it was an experience I had as a neurology resident 10 years ago that really got me thinking deeply about how this technology could be so powerful and useful for people. I looked after a 40-year-old man. It was one of my first rotations in the stroke team. And a 40-year-old man came in, and he'd had a massive stroke. It was actually a tiny part of his brain. He was a father of 3 in the prime of his life. But this tiny little part of the brain called the pons, the little dark region there, that carries all the information exiting your brain. And that got damaged from a blood clot. He couldn't move any part of his body. He could hear, he could see, he could think, he could feel, but he couldn't move and he couldn't talk. He was locked in. And we sat with him and we talked about what this meant, and he was communicating yes and no, left and right with his eyes. And he told us that, well, if there's no cure, I don't want to live like this. And so we supported his wish to be taken off life support. And so I've been thinking ever since then, is there really no other way? Connection is a fundamental human need. And so many of our patients lose the ability to talk, to connect. For years and for decades, they're stuck inside their own bodies. This was a moment with one of our patients reconnecting, and I'm going to come back to this image later on, but this is the power of this technology and the ability to reconnect people back to their world. So for people who have lost the ability to move their bodies, who have paralysis, do you know what the #1 request is? Imagine that you lost your ability to engage in the digital world. What would it be? Well, it's text messaging. Text messaging. And after the last 20 years, you guys have built these unthinkably powerful systems. We can do video conferencing, we can shop online, we can order food, we can do banking, we can do trading, we can manage our finances, we can seek healthcare, all without really moving. But only if you can access the web. So we talk about Web3, the metaverse, democratized access for all, but for 100 million people who can't use their hands, well, they don't have access to that web. So when technology is now needed to fulfill basic human needs, that's not a luxury. That's a fundamental human right. And that's what I think brain-computer interface technology is about. Last year, we became the first company to receive FDA approval to conduct a clinical trial in the US, heading towards FDA approval of the first commercial brain-computer interface company. I'm going to talk to you guys what that looks like, how we got here, what we did differently, and how BCIs are going to fundamentally change the way we connect with technology. Okay, so in simplest terms, BCIs solve the problem of getting information out of the brain to an external device. Now, the way we normally do that is by thinking what you want to do and then getting the information out using the muscles. Muscles in your mouth, muscles in your hand, muscles in your fingers. Because right now, the only way to communicate anything is through your muscles. So how do you get information out of the brain without speaking or writing? Well, telepathy, obviously. I'm joking. Sort of. Okay, first let's consider how the brain works. Actually, how thinking works. And I want to take you to what I found to be an incredibly romantic place where I first proposed to my wife in the Smoky Mountains. Fireflies synchronize their flashing. And it was a mystery for centuries for scientists with how they did that. Ended up being two simple things. One, a firefly has a metronome, which is a beating cadence. And two, the fireflies around one another change, speed up or slow down their beating to get in sync. And they can give the appearance of one enormous organism. Well, that's how the brain works. Individual neurons beat at a certain frequency, and the speed of that frequency is influenced by the speed of neurons immediately around that neuron. So they behave in these groups. And as they beat at a certain frequency, doing a certain function, then that pathway gets laid down stronger and stronger. That's the basis of neuroplasticity, or learning. So it's also called neural oscillations. So the concept, that's the basis of thinking. So the concept for BCI is, how do we get that information directly out of the brain in real time to then convert units of brain activity into a function that can control external devices? That's exactly what a BCI does. Easy, right? Not exactly. So this is the Utah array. This is what got me into the field when I first read about this in 2006. Fundamental, basic breakthrough research conducted using this bed of nails electrode. Incredible work. For 15, 20 years, we've been using this in a very low number, handful of patients, proving this is possible. The challenge is that this requires open brain surgery. And at a fundamental level, we'll get to brain surgery in a minute, but the brain doesn't really like having needles stuck into it. Now, it seems like a glib comment, but it's not necessarily the case in the rest of the body. Look at tattoos. They can sit there forever. There's no immune response. The brain's different. It's very sensitive, and it will continue to keep pushing things out. Open brain surgery, well, that's also a pretty big deal. It's expensive, takes a long time. There aren't many people in the country that can do it, especially the type of brain surgery where you get to particular regions within the brain. It's called functional neurosurgery. About 150 of them in the US. So the question that I've been obsessed with, is there any other way to get into the brain? The answer is yes. We found another way, but we didn't actually find it. It's been there for a long time. This is what it looks like. These are the blood vessels, a naturally occurring road infrastructure that get to every corner of the brain. At the very top there is the superior sagittal sinus, happens to be the largest blood vessel in the brain, right next to the area of the brain that we're interested in called the motor cortex, which is how you control your muscles. Now, the thing is, we actually already know how to get through these blood vessels. We've been doing it for 40 years. If anyone's had a heart attack, there's a decent chance that you've had a stent. So you had a blocked blood vessel, a balloon was put up, stretched open the blood vessel, and then a scaffold was left in place to keep the blood vessel open with blood flowing through it. That's called a stent. I'm sure all of you know someone who's had a stent. So the technology is being developed over the last 40 years to deliver technology into blood vessels in the heart, and we're just starting to figure that out for the brain. The beauty of this is that you achieve that non-immune reaction situation because the blood vessels behave like the skin, and if you leave things on the inside, they get incorporated, and it just behaves like a tattoo. It can stay there forever. So, the breakthrough, one more point. Millions of these stents are placed every year. Millions of cardiac pacemakers are placed every year, not in the operating room, and not by a very low number of physicians, by a large number of physicians in what's called the cath lab. That's where you go to get stents put in, and they're at any neighborhood hospital. So the problem we had to solve was, how can we get electronics onto a stent, deliverable in a scalable medical outpatient situation, and then deliver that into the brain? And so this is what we built. We built an electronics platform onto a stent that achieved the self-expanding properties of the stent and was able to get safely into the brain. So it's connected to a stent. It's in the area of the brain that we want. It's connected to a lead. The lead brings the information out of the brain through a naturally occurring hole in the skull. We're not putting any new holes in the skull. And we're doing it all in a way that's accessible for millions of people. And so here it is. Here it is inside our first patient, Graham, who's very kindly offered to let you see what it looks like inside his brain. And we've just put a little blue highlight over the area so you can see where the lead is coming out of the brain. This was in 2019. It was one of the most incredible moments of my life seeing this image. There's a big build-up to the surgery, to the procedure. This came up on the screen. The device was in. First time in history, there was an electronics inside a brain, inside a blood vessel. And then a couple of hours later, he woke up, asked if he was still alive. He was. And then we got him home. We got him home a couple of days later, and we started working with him and conducting some incredible work over the next couple of years. So here's the system. On the left, you see the Stentrode, which is a stent electrode array connected to a lead. That goes inside the blood vessel, comes out of the jugular vein. That goes into a device that sits under the skin in the chest that has a battery and has a telecommunication protocol using Bluetooth that sends the information out of the body wirelessly. That gets picked up by the white device there on the external side, which is a mobile device, does not have a screen. It does the algorithm processing and then shoots that out to any connected device through Bluetooth as well. This is what it looks like. So the electrodes are the circles on the top of the brain there. Now, the concept here is that when you try to move muscles in your body, we can detect the change in brain signal that occurs when you try to move. And so this is a very simple demonstration of a spectrogram which shows what it looks like in the blue before you're trying to move and in the red after you're trying to move. So we then use our engineering to decode specific movements inside the brain and then turn those into outputs. So the first one that we started with was the foot, because we're right near the foot region in the brain. So we'll ask the patient to try and tap down their foot. They won't do it because they're paralyzed, but we've been able to decode those specific movements. And then we start building out a dictionary, building out a repertoire of different types of movements. Hand waving, maybe finger tapping. We're starting to calibrate multiple different movements. Now these become the building blocks for every single control mechanism that you need to control digital everyday devices. Now we're just at the beginning. This is not an incredibly complicated control mechanism. We're just trying to get a simple, robust functionality to do the basic things. Up, down, left, right, menu, back. The things that let you fundamentally control basic systems that give you power, get back to the powerful platforms. So once we've got one of these movements, we'll then go into a game situation and ask the patient to start practicing using that particular type of switch so that we can get the system getting better and better at that switch. This function allows patients to then use their smartphones, eventually wheelchairs, advanced robotics. But bringing it all together in action, we started with a PC, and here we are with two of our patients. So this is Philip. There is brain signals on the system there. That's streaming out of the body via Bluetooth, and then we've built in functionality to control keyboard and mouse control. We've got different mechanisms given the level of disability for the patients and what system they're using at home to engage with. So Philip said to us once, it's like learning to ride a bike. It takes practice. Now when you think about it, it becomes natural. Now I can email, bank, shop, and message the world via Twitter. At the end, we finally got them onto a group chat on WhatsApp, and we're finding that the messaging was the most powerful thing for these patients. So we had two of our patients messaging each other, and I was on there as well. The term Renaissance was used in the previous presentation by Ariel in regards to space, and I think we're in the same situation with brain technology now. When I started neurology training as a resident, it was the backwater. It was the laughing stock from all the other physicians and not high up on sexy list of what area of medicine you're going to chase. And the reason for that is that you can't fix things in neurology traditionally. You can't fix broken neurons, but brain-computer interface is now bypassing this and creating a direct connection into the brain. I think we're going to see an incredible progress in a range of different conditions now, not just paralysis, epilepsy, depression, stroke, addiction, pain, sleep, headache. We're just getting started. So over the next 20 or 30 years, what's BCI, where's it going? There's been a lot of talk about what it might mean for the broader population, but what I think we're going to see is that BCI becomes a LASIK kind of situation. An elective procedure, takes a couple of hours, makes your brain work a little bit better, you engage with the digital world better than you did before, and you're not coming in because you've got profound injury. Maybe you've got a minor injury, but it stopped your ability to engage with your technology interactions. And who knows where we're going to be in 20 years. So it could be that a small drop-off in your ability to connect technologically could have a huge impact on your ability to behave in the world, exist in the world. And so that's what I think this technology is going to do. Not take us to some cyborg Black Mirror situation, just to bring us back up to where we'd like to be. So just to finish with, this was Graham and Nancy. The moment when he first was able to put his first sentence on the screen, the next hour we put him onto WhatsApp. Up to this point, he had ALS. Nancy was having to try and interpret what he was saying. He couldn't speak, he can't move, he couldn't type. We got him back typing, we got him back onto Microsoft Windows 10, and then he was onto WhatsApp, and all of a sudden she could leave the house again. If you remember that moment when you first got your phone and you first started texting, or maybe the first time you got your car and the world opened up, well, that's what we're trying to offer for the patients whose world has closed down. And there's a lot of people in the world like that. This technology is about the return of autonomy, the return of independence, but mostly it's about the return of dignity. Thank you very much.